guess I'm good to start now. Awesome. Okay, well, thanks everyone for coming to my talk at this droidcon, this lovely droidcon. And today I'll be talking about handwriting recognition for the New York Times Android crosswords. So, a little bit of information about myself. I'm a game engineer at the New York Times. I worked at the NBA, Business Insider, and MTV prior. I have a background in ML and AI research, and these are some of my social links. I'm an Android developer, but I also have, again, an interspersed background in both of these areas, which has led to me working on this specific, very interesting initiative. So, a little bit of a backstory of the project. So, this effort started in the context of an interesting Maker Week project. Maker Week is our internal hackathon that we do at the New York Times for about a week. It's super fun, and really some really interesting things come as a result of Maker Week, and sometimes they become products. People were generally interested in using a stencil to write on the New York Times crossword app. This is possible in the iOS app, just sort of by default, but it wasn't possible in the Android application for several reasons, namely one that we didn't build it. So this is something that I wanted to look into, and also because it was a trickier challenge, we wanted to see what we could do in the span of a Maker week to try to implement this. Kind of took it up as a fun project and a good learning exercise to build a custom solution, but I wanted to really see how far and how deep I could get into it without going too off the deep end in terms of heavy duty AI or machine learning, because we were experimenting with that at the time. And so just to give a little more context, this was in 2023 this started. The machine learning landscape has significantly evolved since then. But so some of these things that I'll be talking about now are kind of contextualized in that time frame. So just to keep you all kind of being oh yeah, you could do this now. I'll go over that as well too, some of the evolutions. So I want to thank some people first before I start getting into the presentation. Who you see on the left is the current New York Times Games team, the Android team. These are my friends, and these are people that I work with. I am working on a different portion of the games than the crosswords right now, but I will say that these people really worked hard to get this app and keep this app going. And if you ever have fun playing any of our games on mobile, on Android, I just wanted to shout out them for being the people who helped support this and who I had the pleasure of working with. And so they're Katie Levitt, Lauren Yu, Joanne Song, Vanessa Johnson, Vasil Moilov, and Eor Shaman. I just wanted to also shout out some core friends of mine who've been very inspirational to me and helpful throughout the entirety of my journey as a developer, and who've just been very contributory to my work. Miranda Fox, who I believe is the most skilled AI engineer at the New York Times. She's helped define the culture of excellence in AI in journalism and engineering. And I'm very grateful to be working with her on a regular basis to help kind of push these ideas forward. Dilek Baikara, an Android engineer at the New York Times, who's my mentee, who's been an inspiration and is endlessly curious about mobile engineering and building experiences for our users. So definitely many inspirational people who've been a part of the journey that have helped me get to and where I am, essentially. So getting right to it, we needed to build the Android mechanism. We needed to build an input mechanism for the crosswords. So as it exists now, if you play the Android crosswords, you'll see that there's a soft keyboard, which is a sort of a custom soft keyboard that comes up, and this is how you enter letters. So this video is just demonstrating that you press letters on the keyboard and they sort of appear in these squares. In order to avoid writing in these, we wanted to be able to write in these squares but not use the keyboard. We actually had to add a sort of canvas-like element, which I termed during the course of development a sketch box. It's really just a custom component that will receive input in a raster and then convert it to a letter through the use of a machine learning model. And so basically, the process of that is what I'm going to go through. So the first tricky part of this, and this is something that a lot of people probably don't think of right away, is that the actual inputting required quite a bit of coordination. And I'm actually not going to go into a ton of the coordination mechanism here in this talk, but I gave a little bit of a demonstration on the right. Essentially, people write at different rates. And if you're writing on a crossword puzzle, or anywhere, some people lift up their stylus. And when they lift, the point is when you lift up your stylus, at some point you want the letter to be translated into an actual character. If you don't time it just correctly, what's going to happen is, as you see on the right, the letter is going to be sent before it's transformed, and therefore the actual letter is going to be incorrect. And so now in the reverse situation, if you spend too long with this, it's going to take a while, and people are going to get frustrated that my letter is not converting to an actual letter. So you actually have to balance the conversion there. And so we built a little bit of a soft locking system. It's just sort of behind the scenes. So I'm not going to go too deep into it. I don't want to inundate people with a ton of code here. That's not the machine learning code. So basically, there's a lock and release that cancels any method currently previously running there. So any other attempt to write in this square is sort of like canceled and muted by this process. There's essentially a locked flag with a delay of two seconds right now. And I'm going to caveat that 2 seconds. But in 2 seconds, you have the ability to start writing your entire character. And by the time you're done with that 2 seconds, the character should be there, and then the input should be processed. So inside the on-touch event, which is actually quite a hefty event for this canvas, so I'm not writing it out here, you're essentially making sure that if your path is locked and the letter has been sent, then you reset the drawing if there's no more drawing to be done and the letter has been rendered. So if you need to draw again on the canvas, you have a fresh canvas as long as it's not been locked. And so basically, again, I just go over the fact that there's a 2 second lock for now. Now I caveated that a bit because that's actually a very complicated thing. People have different rates of handwriting. Okay, like some people write faster than others and expect the results to be rendered faster than others. This is up to more like user testing to determine at what average rate are people satisfied with this sort of like the timing that's necessary. But I'm just putting that aside. I'm just going to go into the architectural components of the system. So this is basically the end-to-end diagram of what it is built. I have this finger up, finger drag, finger stylus listener. That's basically what I kind of showed you. I have the canvas, which is the place where the vector points are rendered and then rasterized. I have the ML algorithm, and then I have the text output. So it should be straightforward from an overall architectural point of view what I'm doing. Now, first, with any machine learning process, and now I want to say this is a different talk than a lot of the Android talks because I'm going to go a little deep into the machine learning part of this. Everybody knows about Gboard and the ability to write handwriting on edit texts and things like that. That's behind the scenes. That's obfuscated from developers. So I'm going to actually go into the ML because that, to me, is actually as equally interesting as the Android development portion. So in order to make sure that you can do computer vision, because this is a computer vision task, you need to essentially pre-process your data. So your data, there are some relaxing conditions to the actual handwriting recognition, which I'm going to be going through. But that basically, the relaxing conditions are people will write a single letter at a time. There's not going to be any connective cursive inside the handwriting section. So people aren't going to be scribbling like signatures, right? That's a whole different problem, by the way. You have to think about things like ligature analysis and other deep handwriting features. We're not talking about that. And so this made us able to use the convolutional neural network model, which is a spoiler as to the model that I used, to allow this handwriting recognition to work. So basically, the input data is a smooth rendered character downsampled to a bitmap image. You can see this license plate process has license plate reduction process has sort of the filters that I've used to kind of downsample the data to the data that can be rendered in the crossword. Now, one thing I do want to caveat is that this has to work for different devices. This can't just work for one phone. And the fact that it has to work for different devices makes this as an even trickier problem, because in certain devices, our crosswords appear really small. And if they're really small, that means you have a limited writing space in that area. So you actually have to take this step of pre-processing very seriously, where you have this grainy, you can assume a grainy or distorted image that you have to essentially binarize, and then you essentially get an aliased version of that image out, and then you have to anti-alias that in order to send that data over properly to your end system. And so that's what I did here. I basically turned all the data to a amenable input for the machine learning model. Now we're going to get to, I've gone through a lot of the Android parts, so if you're not interested in machine learning, you should go. No, I'm just kidding. Stay, please. Okay, so I'm going to be talking about ML and AI integration here. So the first thing I did, because I just wanted to, my background is I have a computer vision background, and when I was doing computer vision a long time ago, I used what are called classical heuristic image detection features. This is before deep learning became a thing. That's a whole different talk, but it's an interesting feature, facet. So I implemented a classical edge detection feature that was engineered with a KNN classifier. Anybody familiar with the concept of KNN, K nearest neighbors? Okay, this is an algorithm I'll show you what the algorithm looks like. I don't just want to talk algo speak without anybody knowing what I'm talking about. So we did that first, and then afterwards we used a pre-built model from Google via MLKit. MLKit is sort of like, you don't have to think about it. It's an automatic model for handwriting recognition on your device. And then finally, we did our own model because, again, it's a learning exercise where we wanted to actually use a convolutional neural network to actually produce the output. I don't know how many people can hear me now, but I hope so. Okay. Okay, yeah. Any better? Or all right. So let's talk about edge detection, the first piece. So the classical edge detection feature required using what are sort of ancient techniques in handwriting recognition. These ancient techniques include things like Sobel filters, canny edge detection, other kinds of heuristic mechanisms. And this is a visualizer I made to kind of demonstrate to you what happens with these. This is something that I built to like demonstrate edge detection. Essentially, canny edge detection, which is this algorithm here, takes the important edges from something and creates like thresholding mechanics so you can isolate what the important edges are. And this is how people used to do computer vision back in the day. People used to use these very specific handcrafted filters. Each of these filters took a lot of effort. This Harris corners, the Shi-Tamasi corners, log blobs, canny edge, Sobel edge. These are all part of a process that is very algorithmic and sort of deterministic, not AI related. So just to give you an idea of the piece of the code that was used, and this is Kotlin Android code as well, but I'm not going to go over too much of the detail, but I'm using a computer vision library called OpenCV to do this work on device. So I took these pre-processed input images, I did all that pre-processing work on them, used OpenCV to run those algorithms that I showed you, and essentially a statistical threshold detection mechanism was used to create these sort of clusters of letters. Now, these clusters determine where a letter should be. Should it be an A, B, or C? So the best thing to do is to like show you the visualization of this. So there's good recognition compared to bad recognition when it comes to cluster detection. As you can see, like these letters are in all sorts of like orientations, and depending on configurations of your filters, you can either have these clusters very separated. So basically, you know when a C that comes in, a new C comes in, should fit into the C category. A new A should fit into the A category, B into the B category, so on and so forth. The issue is that it's not always easy with these traditional algorithms to get good separation between clusters. All right, so you see when the situation is that you have one of the harder devices to do recognition on, the clusters overlap, and therefore you have this sort of like, oh, the algorithm is not sure whether it's an A or a B, and that's where you get confusion. And so here you can see where that confusion manifests in the actual crossword output. So for example, this canny edge detection and other algorithms that I haven't talked about, including histogram of gradients and other key point-based metrics and algorithms that write out the key points of these outputs, essentially perform not so great, right? And that's understandable. It's a first pass, and we have a very unique system where letter recognition, based on different letter styles, people have such variant letter styles that writing a traditional algorithm is just not going to work in our case, and we verified that. So we didn't spend too much time refining this setup. So then we worked with Google MLKit, right? And Google MLKit, again, this was circa 2023. I want to say this was before Gemini. This was before a lot of the powerful ML models came out and became downscaled so that you can actually run these on device effectively. You were essentially allowed to use handwriting recognition models that were black boxed, where you didn't actually see what was going on in the model. There's a convenient API with MLKit that lets you use these models and then just run them. And you can do other things like object recognition, image recognition, etc. Again, state of the art 2023. The model is on device, and it was useful for iOS and Android. That's why it was a nice setup. And this is another nice reason that it was promising to use a model like this, because essentially you had a client-side only integration where this was really the only code. I hid a ton of the code for the integration for the handwriting recognition model in the previous case, because it's just a lot of extra stuff. But in this case, you pretty much have this input listener, this recognizer, and then you have this input and output, and bam, you have handwriting recognition. Okay, so how did that perform? I guess my slide sort of got deleted. No, did it get deleted? No. Oh, my video's maybe not working. Oh, no, it is working. Okay, great. All right, so you'll see that it kind of performs still not so great, because our conditions were very specific to different orientations and different screen densities, that the recognizer did recognize some things, but it often failed, especially when the input was sort of off the baseline. Again, it may have worked better for some cases, but not for ours. So we just wanted to do our due diligence for the pre-baked model. And so therefore, we worked with TensorFlow Lite. How many people have worked with TensorFlow Lite here? Anybody? Okay, great. So so if you've worked with TensorFlow Lite, you'll know that it's now called, there's Lite RT, that's the new version that people use. But TensorFlow Lite is the on-device model framework that Google had built for both Android and iOS to take advantage of models built in TensorFlow, machine learning models. So what we do is we build the model in Google Colab in a Jupyter Notebook in Python. And the rest of my talk is probably going to be Python. So I don't know if anyone's a Python fan, but there's going to be some Python. TF Lite lets you download the model into the notebook, and once you're happy, you get to actually run the model. There's a lot of free custom models that people built. So if you ever get into the idea of on-device machine learning, which I think is a huge thing in the future, and now even, I mean, there's many cases for it, then you will likely want to invest more in TensorFlow Lite. So let's talk about training the model. Okay, so in order to train the machine learning model, right, we need to feed it digits. Now, remember, this is a basic task. Like, for example, if you're an ML engineer, you've probably done some version of handwriting recognition. We're not reinventing the wheel here, but we're combining it with mobile for the purposes of novel investigation in our particular application. That's why we have certain nuances that are different than the standard ML handwriting recognition case. So we take this data set called the MNIST data set, which is basically a list. It's a massive set of different digits, right? Different versions of digits that are specifically used to train the model. This was first effectively solved using LeNet 5 in the 90s, which is a convolutional neural network model that was used many years ago. The just base task of handwriting recognition was solved a while ago. This is an easier task because we're just talking about digits here, and there's only digits 1 to 9 or 0 to 9. So those are this is actually a good canonical test task for your machine learning skill set, I suppose. And again, there's about 60,000 characters in the MNIST data set of varying orientations and degrees and styles in this overall database. So now some people are curious about the model. So here's what the models are. So has anyone used a convolutional neural net before? Heard of that? Okay, so if you haven't, the convolutional neural net is one of the most common machine learning models specifically used for image processing tasks. Almost every computer vision framework uses a convolutional neural network. The structure of the network is on the right, and the idea, and this is actually one of the models which allow deep learning overall to become the powerhouse that it is today, because computer vision was optimized and learned basically by the use of the convolutional neural net and mastered to the point where it's better than computer vision is better than human vision at this point. So the structure of the convolutional neural net is different than the standard neural net in that the convolutional neural net uses the mathematical operation of convolution, which is actually not a very complicated operation, to automatically isolate features within a feature space of an image. So I have this parrot here, and I have these filters here, which are these convolutional and pooling filters. And basically what this is saying is that this structure here understands what this parrot is made out of. Like, if that sounds weird, that's what it is. But that's what the math of it does. It can understand things like feathers, beaks, eyes, etc., just by the math. It knows that these are different structures just by looking at the math. It doesn't know to call it that until it's trained on the fact that these are like feathers, beaks, etc. But once it understands that feature, it understands what a bird is structurally differently than what a cat is. And so this is, again, if you go into the history of deep learning, one of the pivotal moments in deep learning when this particular model mastered this capability. So this is the model that makes computer vision possible. Again, little more structure on the ConvNet. Okay, so the ConvNet is made up of a few different pieces: an input layer, a convolutional layer, several layers, and a standard neural network. This neural network on the right with all these circles is the output neural network. That's the standard. If you ever hear the word MLP, that's this dense layer section. But these convolutional layers are responsible for isolating the images and then downsampling and isolating and downsampling and alternating between those two tasks in order to hone in on different features of this bird or whatever object, and then finally turn that into learning for this dense section here. And we'll go a little bit over the learning process, but the dense section has an output, which is the output of what the object is. So here's another visualization for automatic feature generation in the case of the ConvNet as applied to a face. And this is how face detectors work. You have a face, a ConvNet is applied to extract features from the face, which includes low-level features like curves, color, etc. Then higher level features like parts of the face are extracted, like nose, eyes, etc. Again, the name of these things is not understood to the model. The fact that they're distinct is what's understood to the model. And then you have this high level feature where you have the actual face, and now you have the thing able to recognize different faces. Now, we didn't talk about pre-training or what the thing was trained on, but note that the training helps isolate these features. So now we'll go back to the digit recognition model. We have this client-side integration of this digit classifier. I excluded a lot of the TF-Lite boilerplate and then constructional and the external code because that's not relevant to what I'm talking about. The model itself was relatively small, and that was what was important because this is an on-device small model. We didn't want it to interfere with user experience, and therefore we just, about 100K with the digit recognition model, and even smaller in the modern day. So that's how we essentially are able to justify, oh, this is a nice on-device component. This is a simple convolutional neural net code here. So basically the structure is you have your input layer, as I showed you. You have your convolutional layers. You have your max pooling layers. And this is in TensorFlow, Keras. If this is the framework on Python that's used to do this, you can construct your own convolutional neural network models this way. And essentially, once the model is constructed via the sequential function, the compile function then actually using what's called a categorical cross entropy loss, then actually computes the output of the model. Then the model is, and the structure on the right, these lines here are basically the structure of the model. It's a very simple convolutional neural net. So let's just see when I'm running the model, what happens. I don't know. Oh, sorry, I guess this video is probably, let's see. So when you're running the model on Colab, and because I just wanted to show you Colab, you can see that you have something like 98%. I have 98% on my training data. I input my training data, run the model against the training data, and I see I have 98% accuracy. If you know anything about machine learning, you know to suspect that number right off the bat, because just because you have good accuracy on a specific set of data doesn't mean anything. It just means the model happens to probably be overfit to that data. And so when you see what happens here, we had a lot of training data. I had 60,000 characters, but the results were still pretty bad. Okay, and the reason why is because something was wrong with the actual data. This was a problem that was encountered years ago, and it was solved using a technique called data augmentation. If this thing is actually going to write out the letters, you'll see that like I'm writing out letters and it's still not figuring out what the right letter is. Okay, and so this process is automated. The process that we use to solve this problem is called data augmentation. It's automated and lets us create new letters from these input letters and digits very easily, and I'll show you what that looks like. So what you do is you build a synthetic data set from your initial input. Synthetic data, if anyone is familiar with the idea, is data that you have from real data, and you construct variations in that data. For example, use an algorithm to scale the input data, rotate the input data, shear the input data, translate the input data in different directions, elastically distort the input data, use stylistic variation noise on the input data. All kinds of things I do to the input to make sure that my training set turns from 60,000 characters to 2 million characters. And therefore, I have a ton of training data, and I can capture a ton more variation. And so, again, all these things are what allowed OCR to actually be a thing that is a functional piece. And so this is what it looks like when I apply it against my original MNIST data set. I've applied these transformations, and you can see I took these original characters and did all sorts of crazy things with them on the right. And then the result was success. After data augmentation, I'm able to, and by the way, I'll show you what success is. Let me see if the video is going to play. I hope it is. If it's not, you got to trust me that success is something that happened. But this is only success with digits. What I want to say is that the way this data image generator works, it does small variations in the actual those transformations I showed you in order to make that data actually transform. So we're not doing too drastic variations. We're doing little variations. And again, it's taking a while to load, but trust me that the digit recognition at least worked. Now, the problem is we needed to do full-blown character recognition. And in order to do full-blown character recognition, we needed an extended version of our digit data set. And that digit data set is called MNIST. And so there's a version called extended MNIST, which contains a bunch of letters, as well as digits, and as well as other characters. There's several data sets other than extended MNIST. It's just one set of like extra data. But this model is actually, this capability of ingesting all these extra characters comes at a cost. Like it has a lot of extra training data, but letter recognition is a much harder task than digit recognition. And if you were doing this algorithmically, you would see that building those filters that I talked about before are very, very tough. Like you get like accurate letter recognition across the space of all letters. And so the CNN model is still useful, and this is why another reason deep learning is very powerful, because the idea of deep learning is that you can just take your base model and you can extend it with a few additional layers and increase the power of your model by many-fold just by using a reproductive process of just adding more layers to your network. Now, that's not 100% true all the time, because as your task becomes more difficult, your actual model actually has to become more complicated. You can't just add layers. But for our problem, what we're going to do is we're just going to add layers. And I'll show you how that works. So I just wanted to show you again failure with the digit recognition model. Okay, so I'm running this. Take a second to like run. But you'll see that the digit recognition model against the letter, I'm writing letters here. Letters are not going to work. It barely recognized the A. And the reason, again, is because its brain is trained to only understand digits. Its brain is only smart enough to understand digits. Now, it's trained to understand letters, too. You saw that. I put in the letter data set. But it's still not smart enough to really understand letters because the brain isn't complex enough. So a little bit of a segue into how a model learns in general. I'm not going to go a ton into this, but this is very important because this is the core of machine learning and the core of AI. This is the stuff when you're an AI engineer, you kind of skip over and you're like, ChatGPT kind of magically works and all these things magically work and they like, learn and, you don't have to worry about what's under the hood. But if you care about the ML and the machine learning and the actual structure of the network that makes these results happen, this is the most important slide of all the slides that I've shown you so far just for that purpose. So this model learns to classify characters by comparing its output probabilities to true class labels using a function called categorical cross-entropy. That's a lot of words, but what that basically means is that's a function that lets you detect the difference between two different input data pieces. For example, if I have an A and I have something that looks like an A, the amount of difference between the thing that looks like an A and the actual A is a probabilistic amount of difference, and that's why we call it cross entropy, because you're comparing across two different or multiple different features what the category of the information likely fits into. Now, this is an information theory result. There's a discipline called information theory. Some of you all might have taken it in college, but this idea is that that categorical cross-entropy loss between two input, that is what is important to minimize. Now, in order to do that, right, we need to make sure it's the smallest thing. What I'm showing you on the right is this visualization of this is a completely mathematical visualization, by the way, of what's called a loss surface. This loss surface is a three-dimensional surface of the error of the categorical cross-entropy loss that's computed through this magical algorithm called gradient descent, and in our particular case, it's called stochastic gradient descent. And so what that means, that's an algorithm that says that I am going to, through my entire parameter space, find the smallest location in my loss surface or the minimum loss area of my loss surface that corresponds to the output that I'm looking for. In this case, this loss surface is like, again, a 2D surface on a 3D projection, where you're seeing that the minimization, the stochastic gradient descent algorithm, is descending towards the A. That means that likely what I'm inputting is an A. And the model learns to determine that an A is what I'm using this function, and A is what I'm looking for. Again, it's a little bit, but this is the equation that makes AI work, the gradient descent equation. And modifications of the gradient descent equation are really the, behind the black box nature of everything AI related. Or many things AI related, not everything. So enhancing the model. So basically that model that I showed you before, what I did was that I enhanced it by adding a few more layers. So I just added another convolutional layer, another max pooling layer, and another dense layer. I kind of skipped over fast for the interest of time what the layers were, but the max pooling and convolutional layers you can think of as the layers that inflate the data to convolve and like smear across other data nearby, some of the AI stuff. And then the max pooling layer reduces and focuses in on parts of that data that are important features. So it's kind of like a lens that's tuning in and out and zooming in and out on the part of the data that is important and consists of an actual feature that we care about. And so again, I really didn't do much. I just added a few new things like dropout, and don't worry what dropout is. Dropout just means like the network kind of destroying its own brain in order to like learn better, for the lack of a better way of saying it right now. But the interesting thing is that even that by itself wasn't enough. We have to find the parameters of the network that make it actually able to learn better. So this is done through a process called cross-validation. I'm going to ask, has anyone heard of cross-validation? If you have some ML background, you probably have. But cross-validation is another technique which allows you to kind of look at your entire space of parameters and basically try your model against different sets and mixes of data. This is very important because a machine learning model is only going to work if it's not only true for one slice of your data, but it's also true for several pieces of your data that are smeared through. Like you have to mix your data and try it against different variations. And so that's what this cross-validation is. And that's combined with this process of parametric grid search. So this parametric grid search actually searches for the optimal parameter set, which minimizes the loss. So again, I don't know what the parameters are. It could be like, of this network, there could be like 5, 10, 15. I don't know what the number is. But if you try a bunch of numbers against a bunch of mixed data sets, eventually you'll find the right combination of parameters that makes the network perfect in order to recognize letters. That's basically at a very high level the idea that I've kind of also minimized a little for the interest of time. But this function this is in Python land upstream, is actually computing this a parametric grid search, which is actually a very slow process. But if you do, there's many optimizations to this that make this faster. But what I showed you here is kind of like the base, like if I have a certain number of parameters, this is the base brute force version of it. But again, we used actually a more powerful version. And so the end result is that we have a better recognition model, which recognizes letters. Is my mouse here? Yeah. And so basically, skipping to the fun part of this, so we're able to get success. And see, as you can see, I'm writing letters down, and all of them are being detected perfectly. Like just as good as Google at this point. No, I'm just kidding. But like it's it's still pretty cool. We have this ability of machine learning from front to end, and so we have again. This is essentially what we really like to do, but I wanted to create a note on synthetic data here. So has anyone heard of the mode collapse hypothesis? That essentially AI is going to eat itself? Okay. So basically, there's this idea that AI is going to train itself constantly on its own data so far that there's no more unique data until there's only AI-based data, and it's going to train itself so much that this theory of mode collapse occurs, which is totally true in smaller data sets. Like mode collapse can totally occur. And what I did is I overtrained this sort of synthetic section on synthetic data. And you can see all these letters automatically basically turn into the same like oblique structure that's very hard to understand. And so this is the visualization of mode collapse. We've even written about it in the Times as a potential hypothesis for the, sort of end of world AI scenarios or whatever. I mean, there's different ideas and it's an actual real thing, but the truth of it is that we have to consider things in different terms. And people have been essentially, for a long time, AI researchers have been figuring out ways to prevent mode collapse from occurring. So now if you're familiar with this work, you'll see, not to counteract those large scale like doomer theories about things, but just understand that there are ways that this will not occur. So I just wanted to highlight this out. And so next steps, this was a while ago, is that we want to essentially do more on-device tuning. Now, the newer Android ecosystem, the newer Android devices have what's called AI Core on them. Does anyone know what AI Core is here? Okay, so AI Core is a centralized machine learning on-device framework that, as of Android 14/15, it came out and it can actually do centralized on-device machine learning that's private to the device. And machine learning, I mean inference, not necessarily training, though you could do training, you don't want to do that. You are doing the output of machine learning models through the centralized AI Core, and you can use that with Gemini and Gemma and several other local models. So basically what we could do is like potentially if we extend the feature, we could do other things like scribble to erase detection. We could do more advanced handwriting analysis. I wanted to talk a little bit about the vision. I'm running out of time, so I wanted to talk about the advancement of the vision transformer model, which is another advanced model, which is an advancement over the convolutional neural network model and has basically the transformer. If you're familiar with the transformer, has a vision variant, which does a lot of this work. So again, handwriting recognition has been solved using this model as well. And so back to the Android world a little, you can use the ML kit now if you want. And I have a sample project on my GitHub that I threw together to like actually demonstrate the use of this ML kit to do this, but you can use this digital ink recognizer. If you don't want to do any of the complicated things that I did in order to train my own model to do this, and you just want handwriting recognition on squares, you can do this through the current day ML kit. And this is a Compose app that I wrote that has these little squares, and using the digital ink recognizer, it can do very pretty decent handwriting recognition. And again, one of the things that we would want to do if we actually extended this further is create like a self-training mode. We want to do things like, also I create a QA mode because essentially whenever the model happens to be incorrect, we could actually be like, oh, this, you can report the results of the model upstream. And that's a very important thing in machine learning in general. You want to be able to monitor the performance of your model. And that means oftentimes taking user feedback to monitor the performance of your model in applications that involve machine learning. So I created, again, this view that's like what letter is often mistaken for what other letter, and therefore you can create accuracy percentages, which you can send upstream and then reinforce the model in order to perform better. And so that's basically my talk. I think I'm at the end of it. So I guess anyone have any questions or anything? Thank you. Awesome. Cool. I'll just stand here till anyone thinks of anything. Or I'll head to the bathroom. Oh, go for it.
So I was just wondering, like, how much of a challenge would it be to target like other languages which may or may not use Latin script?
Mm-hmm.
Like, where would the obstacles be with that?
So at this point in time, I think so the question was, where would the obstacles be at this point of time if we were to try different languages? And that's a very important question. At this point in time, the obstacles would be essentially there wouldn't be too many, because the digital ink recognizer models that are already present can do that. It can target other languages. So if you wanted to try, but if you wanted to, again, do the learning from scratch, it actually becomes a lot more complicated. And there's a point when your on-device model might not actually suffice to handle all the languages in the training. In that case, because you have to consider that the size of the model and the latency of the model is important. So if that happens, then you have to actually get a smarter model on your device that can do this stuff, or you're going to have to come up with a different process. And so again, training a model to do that has been done, but then it depends on your application on how the challenge is to make sure it fits in your product requirements, to make sure that the app is not slowed down because of it or something like that. But as with all things AI, that changes over time, so that'll improve over time as well.